Hello? Now it's time for problem 6. It's only about this curve, but we need to find conditions for having points of order, or for the points of order 2, 3, and 4, like we did for, I think, was problem 4. I haven't prepared that, so I wanted to derive those expressions while recording. And I think we should do it rather for the more general form, so we don't have to go through all the details again. So points of order 2, of course we have the unit element, and that's the only point at infinity. And then the other ones have vertical tangent. So if we define f of x point y point z to be y squared z minus x to the third plus a z to the third, then the derivative with respect to y must vanish. So y itself must vanish, or z. And when y vanishes, that means we must have third roots to a. So it's the points and there may be, if the prime, or we can just say any finite field q, if q is equal to 2 modulo 3, then the square root has one and only one solution, so there's only 2 points of order 2. If it's equal to, q is equal to 1 modulo 3, then we will have a third root of unity, but not necessarily of a, so in that case we'll have none or 3 points of exact order 2. So that's that. So those are found by the inflection points, and of course there is one at infinity, the unit point, which turns out to be, or that's obviously an inflection point, of course. And then the Hessian I computed in another video, so I just want to copy it. Now where do we put it? Do this. The Hessian times z itself, 24x times x to the third minus 4a z to the third. Here I have, it's not really the Hessian because I have reduced by setting this to naught. So it only holds for points on the curve. One possibility is x vanishes, then y equals minus square root minus a. Maybe 2 points. And we already have the unit point, so we can just set z equal to unity. So it's third root, cubic root of 4a, and then if x to the third is 4a, then x squared is 3a. So if the cubic roots and square roots exist, we have 6 points here and 2 here, that's 8 altogether, so there are 9 points possible, as it should be. And whether these roots exist, we'll have to see. 3, that's point of order 4. And we'll use the same computation as I did a few exercises ago. So we need all the points that end in some point of order 2. So we choose 1/3 root, 1 cubic root, t, and then once a point, x point y on the curve, whose tangent goes through the point G point naught. Could you please stay away? There we go. And I copy y divided by, that's delta y divided by delta x. That I have the points here, so delta y from there to there, delta x from there to there, should be equal to the slope of the curve. So that gives 2, we'll just write that as t to the 3rd divided by x minus t equals, and the derivative is 3x squared. What do we have here? It must be a homogeneous equation, of course, because this expression is homogeneous. And we take the discriminant. It's 16t squared minus 16t squared x plus 2t squared that was a surprise. I need to take a break and check that this is right. It's really a surprise to me. Oh, we can check the number of points of order 4 maybe. There can be at most 16, and there must be able to be at most 16. So we shall have up to 4 points whose tangent goes through the one chosen point of order 2. And if x is minus 2t, then y squared equals minus 8t to the 3rd minus a. t to the third was a, so that's minus 9a. So we get 2 points, and we should get a possibility of 4. So I've made a mistake, and apparently I always do. Just make a break and check it. That was easy. Y had to be squared, but not 2. So we move it. It still doesn't want to work. No way. So we move it to the right side. X squared. That was slightly too small. X squared minus 2xt minus 2t squared. I set 2xt and then it refuses to write it. The discriminant now is 4t squared plus 8t squared equals 12t squared. This number 3 comes from differentiation, and this must give, I should correct this as well. It still doesn't write. It's run out of ink. 2x to t and 3 minus 2. Yes, I think that's right. So it's 2t plus minus square root of 3 times 2t divided by 2. So it equals 1 plus minus square root of 3 times t and then we need the equation for y as well, or should we compute it explicitly? Let's see if we can make a general condition. So x to the third minus a, well, let's see. So it's t to the third one plus minus 3 square root 3 plus 3 times 3 plus minus 3 times square root 3. So the first, it's a binomial formula. First this to the third, then 3 times this squared times this guy, then plus 3 times this guy times that one squared, and finally plus this one to the third, the cube of it. Then we need to subtract unity, and we have a 1 cancel, 3 tends to 9, plus minus 6 square root 3 times a. So that was y squared. All right, I don't think we should use that. That was the first part. Now we start. Of course, the prime 3 is excluded because it has bad reduction. So we start with 5. And it's congruent to 2 modulo 3, meaning that the group of additive points, let's call it G, has 6 points. That means that it must have 2 points of order 2 and 2 points or 3 points of order 3, so the type must be 2.3. And does it agree with what we've found here? First of all, A is unity, so there is only one square root of 1. There's only one cubic root of 1, and that's 1. So there are 2 points of order 2 and points of order 3. This exists, so we need to, and naught exists, so we need to check whether there's a cubic square root of minus a, of minus 1, or of 3. And the only square roots are plus minus 1 when p equals 4. Oh, minus 1 is the square root. So that means that we have 2 points with first coordinate naught. So that should be it. I'll just need to find them. So it's the square root, that's plus minus 2. So it's naught point plus minus 2. So that's correct. P equals 7. Here we need to find out the number of points, and I've prepared that was the wrong guy. I prepared the Maple script here, and I haven't prepared it. Oh, P equals 7, that's the one we need. And then minus unity. And let's get the squares. 0, 1, 2, 4. And then the points, number of points on the curve. 1, 2, 3, 4, 5, and then the point at infinity, 6. Back again. We have 1, 2, 3, 4, 5, 6 points all together. So the type must be 2.3. And let's just check the point of order 2. That was something 0.0, of which we had 2.0. So 2 to the third, that's 8. That's plus 1. That was A. It's the root of unity. Why don't we have 3 roots of unity, by the way? P.7, it's 6 plus 1. I think I claimed that when P is 7, we should have 3 roots of unity, 3/3 roots of unity. One, 2, 3, and then we need to go to 6 as well. I should have done. Yeah. I don't get the multiplicity here, of course. So let's. Oh my God! Now that was the one we needed. And next, let's make a sequence. Now we get the multiplicity, and one unity. There are 3 cubic roots of. There are 3 what is it called, cubic roots of unity, and of -1 as well. All right. Strange confusion. The next guy is 11, and that's 9 plus 2, so we have 12 elements. We need to find out how many roots of unity we have, and against that's how many square roots of cubic roots of unity we have. Did I say square roots? It looks like a cubic root here to me, and that should be only 1. So there should be only 1 element of exact order 2. I claim therefore that it's 2 squared. The type is 2 squared 0.3, so we have 2 points of order 4. So let's check that we do have 2 points of order 4. The condition was that there was a square root of 3, cubic root of a, of a. So let's find those. The cubic root of a, we have come to 11. And there's only one cubic root of unity, and that's 1. So we only have one unit as claimed. And we can see that x maps to x to the third is 1 to 1. And the number of points, 1, 2, 3, 4, 5, that gives 12 altogether. Do we have a square root of 3? Yes, we do. I would like to make a table as well. So plus minus 5, that's square root 3. It's 1 plus minus square root 3. Minus 4 and 6. And one of them should be a square. It's now minus 4, that's 17, no. And 3, that's a square. I already knew that. Oh, it was 6. Minus 4 or 6. None of them are squares. I believe I've made a mistake. So we just compute f of oh, that was the two x values. We need those first. That was 1 plus minus square root through. So it's the ones I need to compute for y squared. That is 9 plus minus 6 square root 3. This was the x values. Oh, never mind. let's do that on Mabel and then check the result I get when I insert in the formula above. 9 plus minus 6 . This is weird. That was the plus minus I already had, so plus minus square root 3, that's just 5. $39, that gives 6, and minus 23, that gives minus 1. No, it's minus 21, which gives unity. Let's just check that that's correct. One and 6. Wow! I made some calculations that might be right. And 1 is of course a square, and I hope 6 is not. It's not. So it's verified. We do have 2 points of order 4. We didn't need to do that, but I wanted to check all my formulas and everything. That was Q equals 11, now 13. That's 1 modulo 3, so we need to check the number of elements. One, 2, 3, 4, 5. Now what's that? How could naught ever work? That's the wrong guy I'm checking here. It's the wrong number of elements. Now this makes sense. 1, 2, 3, 4. That's 8 plus the 4 of order 2. That's 12. So we had 12 points. Again, we need to check the number of... No, we don't. We have 4 elements of order 2, so it must be 2.2.3. That's 18 minus 1. We need to check the number of points of order 3. All 9 may have order 3, or there may only be 3, and then 6 of order 9. We just go through the same computation to check the number of elements of order 2. There's only the 1. To check the elements of order 3, we need to check square roots of -1 and 3. we do have a square root of -1, and we don't have a square root 3. Therefore, we have exactly, here, 0 plus minus square root 1. So we have 2 points of order 3. And we will just write them up. I forgot what is it. 0 plus minus square root -1. And square root of -1, that's 4, of course. If I'd been a bright guy, I should have known that. And I don't have a way to check that, so we just believe it. It makes sense. And that means that the type of the group is 2.3 squared, 2.9. 19. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 24 plus 4, that's 28 points. Lovely. And as far as I could see, we have 1, 2, 3. That's no coincidence, of course. We do have a third root of unity itself, and since the multiplicative group has 18 elements, it does have a cubic root of unity, or 3 roots of unity. So, of course, we have 4 points of order 2, and that makes the type 2.7. And the final guy will have 24 elements, and this is 8 times 3, so there's only one possibility. We do have a question about how many points of order 2 we have. Now, do we know anything about that? Points of order 2. Actually, when I look at this, it seems it was 23, so it's 2 modulo 3. So x to the third, x maps to x to the third is 1 to 1. That means we have only one point of exact order 2. Therefore, it must be 8. The type must be 2 to the third, 0.3. And that means we have a generator of order 8. We have a point, so that 8 times the point is unity. And that means we have P, 3P, 5P, 7P of order 4. I think they have order 8. Two P and 6P have order 4, and 4P have order 2. So I want to verify that we have exactly 2 points of order 4. Just to make sure that I've got everything right. Therefore, we need a square root of 3 first. There's no square root of 3. Or maybe I didn't do the calculation here. No, I didn't. Three is the square root, and I wanted to know, it's 7. The square root of 3 equals 7. So the x values are 1 plus minus 7. And 9 plus minus, I'll just let Mabel do that. F of something minus 6 and 8. Thirteen and 5. So I claim that one of these points is a square modular 23. Now what was it? The points were 5 and 13. Neither seems to show up. Oh, 13 did. It's right here. So we have exactly 2 points of order 4 as stipulated. And that means that I have found the correct type. All right. I have to be very careful when doing these things, as you can see, and they are not particularly difficult, but so many different things need to be combined, and I don't have them available on different sheet of paper right in front of me when I'm recording, as I do when I'm working on my normal table. So this is actually difficult. On the other hand, it's very fun because it is quite requiring.